Hey there, fellow lovers of proofs. I hope you are well, and I hope you're enjoying all of the different things that come with an unprecedented season of life, such as this, and learning new things that you wouldn't learn otherwise. I hope you're wearing your math shirts too. Math clothes make you feel better, so I thought I'd show you uh, my math shirt of the day. Avoid negativity. Anytime you're wearing something like this, or socks or pants or something that reminds you of things that you love, like mathematics, it's going to make everything better. Plus, my son said, "Hey, Dad, if you grow a beard, you'll be awesome." So I thought, why not? And I don't know if it's working or not, but here we are. Also, my hair is growing out really long, so now I have to wear a hat, or I have to do my hair every time I make a video. Who wants to do that? Hair is overrated. Uh, let's see. Oh yeah, we should get back to class. We're starting chapter 5. 5.1 is about sets and set operations, doing things with sets. Yeah, because there's so many different little definitions and little activities that we perform with sets, and there aren't very many proofs in section 5.1. I'm making this video on Zoom because I can share my screen with you, and I created a PowerPoint that I'm just going to talk through. The reality is, probably you can read through the section and learn this stuff pretty well, but I thought I would talk through it a little bit. And I'm just going to kind of walk through the section. Then what happens on Tuesday is that you can just send me questions that you might have, particular problems. I know that I'm assigning number 17, and number 17 is a proof. Yeah, actually, the first part of 13 is a proof also, and I assigned that because I love proofs. But most of the problems are pretty straightforward and just learning some terminology and set operations. So let me start this by walking through our PowerPoint. We're taking groups of elements called sets. Here we've got a set A and set B with some different elements, and we're going to talk about putting them together with addition, which is called union, our OR operator from before. Sometimes we want to know what elements are in both sets. So that would be the intersection of the sets. And we're also going to look at the opposites of sets, or the not sets, which are called the complements of sets. And so you can see here, of course, you can pause the video whenever you want. You can look in the book. I just pulled these from the book. But we're going to be putting sets together and separating sets in different and interesting ways. The intersection, this is a formality of sets A and B, written A intersect B, that's our AND operator, is the set of elements that's in both A and B. So we could read this A and B, and in this set builder notation, we would say A and B is the set X elements from a universal set such that X is an element of A and X is an element of B. It's just another way to read it and name it with precision. So that's the intersection of sets. This would be the union of sets. Think of union as an add. Whatever A union B is means you take everything in A, you take everything B, you glump them all together, and that's the new set A union B. You can see formally that's the set of X's from the universal set such that X is in A or X is in B. Pretty straightforward. Then we talk about some different subsets. We talk about A minus B, the difference or the subtraction of sets. So A minus B is what you think it would be. It's set A, and then you take out all of the elements of B that happen to be in A. So formally speaking, A minus B would be the set of elements from the universal set such that X is an element of A, X is from A, and X is not from B. So we took all of the elements that were in A that were also in B out and have a new set. The complement of set A, written A with a superscript C and read the complement of A, is the set of all elements of the universe that are not in A. So basically you just exclude everything from A, and whatever's left over is A complement. Maybe you've heard this before. A lot of books have different notations for the opposite of A. Some have an A with a bar over the top. Some have an A prime. Some just say not A. So it depends on the book, but our book is using A complement with this little C. I'm going to give you a couple of activities whereby once I describe them, I'll have you pause your video and take a look and see if you can create some of these things. It's good practice for the homework. And then when you resume, I'll have the answers on the next slide. So we've got this universal set of integers from 0 up to 10. A is some of them and B is some of them. Specifically, this is just an example of using an operator. A and B would be the set of elements from the universe, which is integers from 0 to 10, such that X is from A, but also X is from B. So we're just looking for what matches from both, and 2 and 3 are in both. So the activity here is 7 different problems where you're using the roster method to specify each of the following subsets of U. So go ahead and pause the video and try to write out kind of what they wrote out here, and then we'll resume in a minute and take a look at the answers. So go ahead and pause. All right, glad you're back. That was fast. Here's what I got. So A union B is A or B. It just means you're taking everything in A and everything in B. You're clumping them up all into a set. Union just means you get all of this. You also get all of this. So it's just an addition. It's a sum total. Notice you never write repeated elements twice. Once an element is in, it's in. There's no sense in writing redundancies. A complement would be everything not in A, but in the universe. So we would take A out of the universe, and then this would be what's left, A complement in red. B complement would be everything not in B. So you look at the universe, you reduce it by B, you subtract B out of it, and then this is what's left. A union B complement, you would take everything in A, and then union is like an addition. Then you're just going to add some more things. What are you going to add? You're going to add everything that's not in B that's in the universe. So union is a nice operator because we don't really have to think very much. We just take everything here, and we put them all together. Intersection is where we have to look for the commonalities and only put what is in both. So down here, A complement intersect B complement. Well, we've actually already made A complement in red up here. We've already created B complement in blue here. So A complement and B complement would be the elements that are in both, the overlap of those two sets, the blue and the red, which happens to be 7 and 10. Number 6, A complement union B complement would just be everything we wrote down here, everything we wrote down there, all put together into one set. And finally, we have some operators in parentheses. So A and B would be the intersection of A and B, but then we have this complement out here, which means not. So it would be everything else, everything else. So A and B was 2 and 3, but the universe is 0 through 10 integers. So you see that if you take out the intersection 2 and 3, what you're left with is the integers from 0 to 10, excluding 2 and 3. So hopefully that worked out. Straightforward, not too bad. We also like to make Venn diagrams to talk about different parts and pieces of sets. So we've got some regions here, and this is not the element one, this is region 1. That would be the part in A that's not in A intersect B. We've got region 2, which would be A intersect B. You could see this region 3 here is in B, and it's not in A. So if you ever want to subtract something when you're writing out set notation, you could say like all of B, and then if you say and not, whatever you say after that is the thing that you're kind of subtracting out. So we're going to be running into trying to make statements about particular regions. So A and not in B, we could say it A minus B, or we could use some operators. A, use the and symbol, and then we could say B complement because that would be not in B. A and B is the intersection, that's region 2. B and not in A would be region 3, and we could write that B minus A. Or not in A and not in B would be region 4. You aren't in A at all, you aren't in B at all, so you must be just outside of those two circles. I think that's pretty straightforward. You've probably seen that before in other classes. All right, second activity, we've got A and B. This is the diagram, the shaded diagram for A union B. And then you're going to do something like that, but for different things down here. So go ahead and pause the video and see if you can make some drawings of these different statements 1 through 6. Again, you guys are super fast. So let's see, what do we have here? Number 1, A complement would be shading everything outside of A, and there it is. A complement union B, again, union is nice because you can shade all of the first thing, also shade all of the second thing, and then just let it be. So A complement would be everything outside of A. So everything outside of A is being shaded, but then I'm also going to shade all of B, but I've shaded most of it already, and then I just finish off shading B. So I get that little sliver right there. A and B complement, first I'd look at A and B, which would be this intersection, but I didn't shade that, and I shaded everything else because I have this complement right here. B complement is everything outside of B. A complement, union B complement would be everything outside of A, everything outside of B put together. The only thing that is not shaded is this part in the middle that is both A and B. And then finally, A union B would be all of A and B, but then I'm taking out, I'm subtracting A and B. So you see I took out that. I didn't shade it. A couple more definitions. A and B are two sets inside some universal set U. A is a proper subset of B, provided that A is a subset of B, but A isn't B. And we can write this terminology without the sort of equal to looking bar to mean that A is a proper subset of B. Of course, if something is a proper subset of B, if A is a proper subset of B, then A is a subset of B. So you could write, if you can write this, then you can write this. But writing this is not necessarily going to allow you to write this, because if A is a proper subset, again, there's something in B that's not in A. A is not fully B, if that makes sense. A couple more terminologies and a little bit of logical operators here. So A being a subset of B, not just a proper set, but a subset of B, means for all X from the universe, and here's an if-then statement, if X is an element of A, then X is also an element of B. To negate that would be to negate all of this. So if you remember back from early on in the course, firstly, we need to negate the for all. So not all of this. The negating of the for all means there exists. So if it's not true for all, that means there exists some element in the universe. And then we have to negate this conditional statement where not, if then. Well, to negate a conditional statement means you actually get an and statement whereby we say the if part is actually true, it's present, and the not of the then part is also present. So A not an element of B means there exists an element from the universe where X is an element of A and X is not in B. That means A is not a subset of B because there's something in A that isn't in B, which makes sense intuitively as well. All right, do we understand all of this? So given a universal set, just integers from 1 up to 6, and A and B and C being subsets of those three, and by the way, you might just simplify C a little bit because that's a fancy way of saying something not very complicated. But we're going to fill in blanks with one or more symbols, proper subset, subset, equal to, not equal to, is an element of, or is not an element of, so that the resulting statement is true. It says for each blank, include all symbols that result in a true statement. I actually didn't do that. Every time you can write a proper subset, then you can also write subset. So just note that that is a directional thing that can be present. So go ahead and pause the video. Try to fill in some evaluators or some comparators between these two things. And come back in a minute, we'll check your work. Marvelous. The first thing to note is that the set C is x is from the universe, which is just integers from 1 to 6, such that x squared is less than or equal to 2. Well, the only one that's squared and less than and equal to 2 is the element 1. So C really is just a set with the element 1 in it. And I got these things. A and B, not the same. 1, 2, 4, 1, 2, 3, 5. Not the same. And A is not a subset of B. 5, how does 5 compare to B? Well, it's in B, and so 5 is an element of B. Here they're asking us to compare A and C. A and C are not the same. Actually, C is a subset. It's a proper subset of A, but it looks like in our book, they're not letting you kind of turn around this subset thing to go the other direction. So I just had to write A is not the same as C. 1, 2 is a subset of A. It's also a proper subset. 6 is not an element of A. This is the empty set, is a subset of B. By the way, the empty set is a subset of any set. And then a set is a subset of itself. So that's a theorem in our book also. Here we've got, and notice when we have brackets here, that actually means the set 5, whereas over here, this means the element 5. So the element 5, the element is an element of set B, but over here, we've got the subset 5, or 5 as a set is a subset of B because it's a part of B. What else we got? 1, 2, the set 1, 2 is not equal to C, even though C is a subset of 1, 2, and C is also a proper subset of 1, 2, because C is just 1. 4, 2, 1, the set 4, 2, 1 that is equal to A. They have the same elements. And B is not equal to the empty set. But we could say that the empty set is a subset of B. Then it gets more interesting. If we have 3 sets, A, B, and C, where they may or may not overlap, and then we name all of the overlapping regions with numbers, of course, always in some universe, because you might be outside of all 3 sets, we can start naming and drawing and shading different portions of these Venn diagrams. So go ahead and pause the video here and try to make a drawing. You can see right here, this is really just A and C. A intersects C is being shaded, but down here, you'll draw your own and make your own shadings to make sure you understand this, this language, how these terminologies match a particular picture and regions from that picture. So go ahead, pause the video. And we're back, and it looks like I forgot to include the picture of the solutions there. So for whatever reason, I will just have to show it to you. So here's what I got. And if that doesn't make sense to you, then we can talk about it on Tuesday when we meet. A couple more things and we'll be out of here. I pulled this paragraph from the text. It makes the distinction between the symbol is an element of and the symbol subset of, which are 2 different things. So for example, the number 5 is an integer, so we could say 5 is an element of the set of integers, but we would never say that 5 is a subset of the integers since 5 is an element and is not a set. However, if we have 5 with the brackets around it, then that means the set with 5 in it. So we could write that 5, the set, is a subset of the integers, but we would never write 5, the set, is an element of the integers. So it's an important distinction that we don't want to confuse. 5 and the set 5 are not the same, even though they kind of look the same. They have a different meaning, and we interact with those things differently symbolically. So make sure to understand that distinction. Power sets are interesting. Power sets are sets of sets denoted with this italicized capital P that looks cool. P of A would be the power set of A, and it's a set of sets. So X is a power set of A if and only if X is a subset of A. So what that means is if I give you a set A, then the power set of A will be all sets that are subsets of A. Of course, the empty set is a subset of any set, and then all of the set is its own subset. But then there are other combinations that will be subsets of a set. So the power set of A, if A is the elements little a and little b, would consist of the empty set, the set AB, but also the set A and the set B. So there are 4 elements or 4 sets in the power set of A. Another example, if B is a set with elements little a, little b, and little c, then the power set of B would consist of 8 sets. The empty set, of course, the ABC set, and then every set of size 1, and every possible set of size 2. But every one of these sets in the power set is a subset of B. So a new definition to play with, and number 17 on the THQs is related to that. So that'll be fun. Number 17 is actually the proof of this theorem 5.5. N is a non-negative integer. T is a subset of some universal set. If T has n elements, like the set we just looked at had 3 elements, then the power set of T has 2 to the n subsets. So we had 3 elements, and we found that the power set had 2 to the 3rd, which was 8 subsets. And this is going to be true no matter what. And you're going to prove it in exercise 17. If you want to look at it on Tuesday when we have class together on Zoom, we can do that too. But an important theorem from this section. And one last thing, if we count the number of elements in a set, that is called the cardinality of the set. And it's denoted by this author as card A, card A. So the cardinality of the empty set is 0 because there's no elements in it. The cardinality of set AB is 2 because there's 2 elements in it. And the cardinality of the power set of AB is 4 because there's actually 4 sets within the power set of AB. There's the empty set, there's A, there's B, and there's AB. So there are 4 sets. That's the cardinality is a count. So hopefully that helps. And I want you to, if possible, view this video and try the homework questions. I've updated the assignment sheet, and send me questions that you might have before Tuesday so that we can address those during class. Thanks so much, and I hope you're having a great weekend.